Okay, so for the second video for chapter 5, we're going to look at double displacement reactions. So first thing is, when we have a salt like sodium chloride that's marked as aqueous, ionic compounds dissolve in water by dissociation. They split their ions. The sodium ion, the cation, separates from the chloride anion. And a salt that dissolves 100% and dissociates 100% would be considered a strong electrolyte. Electrolyte just means ions, so if this produces a lot of ions in solution, it's a strong electrolyte. If it's weak, like a weak acid or a weak base, or something that is not fully soluble, then it would be a weak electrolyte, because then there wouldn't be that many ions in solution. And that equilibrium of how well something dissolves or how strong an acid is something that we talk a lot about in Chem 2, so we're not really there just yet. Just understand for now that a weak electrolyte means there's not a lot of ions in solution. And then there are compounds that dissolve in water, like sugar, but not because they ionize. Sugar is a covalent compound, so there are no ions. And so if there are no ions, there's no electrolytes, right? And you may remember from Intro Chem the electrolyte test we did where the light bulb came on if there were ions in solution that could carry the electric current. If you don't remember that, don't worry about it. But basically, the more ions that are dissolved in solution, the more electrolytic it is, right? So what we look at with double displacement reactions, these are reactions that either A, are acid-base and form water, or B, they form what are called precipitates. And precipitate is just a fancy word for an insoluble solid. So what happens in these reactions is you have some kind of ionic compound AB that's dissolved in water, and you have a second solution with an ionic compound CD dissolved in water. And what you predict is, and you can kind of see this, right? A would be the cation, B the anion in that first compound. Sorry, let me move that up. And then C would be the cation, D the anion in the second compound. So if we had something like sodium chloride, the sodium ion and the chloride ion, those would be separate, right? They'd be floating around in the water separately. And what we predict here is that A will go with D, right? Because positives and negatives go together. And the C will go with B. Same thing, positive and negative will go together. And if the reaction forms a precipitate, one of those two compounds, sometimes both, but usually no, would form a precipitate. All right, so here's what we would look at. In your chapter 5, table 1, there is a list of solubility rules that will tell you what forms a solid and what doesn't. Now this table is not something you memorize. I'm going to give you the solubility rules, and this is what it's going to look like. So they are listed in order of importance, right? Rule 1 trumps rule 5 or whatever, but basically the first rule is that salts, and salt just means any ionic compound, that contain group 1 alkali metals like sodium are always soluble. Salts containing ammonium, NH4+, are always soluble. Salts containing nitrate are soluble. Acetate, soluble, and chlorate, soluble. Right? When we get to the halogens, chloride, bromide, iodide, those are mostly soluble, but there are some exceptions. Silver chloride, silver bromide, silver iodide, that's insoluble. Lead 2 chloride, lead 2 bromide, etc. These would be insoluble, and those would form a precipitate. So we would see some kind of cloudy substance form if we had a solution containing chloride combined with a solution containing silver ion. Those two ions would come together and form a precipitate. Silver in general is typically insoluble, but again, not with nitrate or acetate or chlorate, right? If silver's with those three, it's still soluble. Sulfate, SO4, these are typically soluble, but again, the exceptions here, a lot of the alkaline earth metals, and then again, silver and then lead. Hydroxides are slightly soluble. That means they don't dissolve very well. So we would mark those as precipitates, except, of course, when they're combined with alkali metals, right? Alkali metals are always soluble, but hydroxides are typically insoluble, especially when you have group 2 alkaline earth metal, alkaline earth metals, sorry. A lot of the transition metals, those would all be insoluble. Sulfide, S-2 of the transition metals are insoluble. Carbonates are typically insoluble, chromates, phosphates, and then fluorides. So we're going to do some practice examples and look back at these solubility rules, and these are going to be posted also in the Chapter 5 folder. So first question we have here, we've got sodium nitrate reacting with magnesium sulfate. Both of these are in solution, and we want to know if a reaction will occur. So when I look at my first compound, right, my cation is the sodium, my anion is the polyatomic ion nitrate. In the second compound, I've got magnesium cation, and I've got the sulfate anion. And what I'm looking to do is first, figure out, would sodium and sulfate form a precipitate? And the answer is no, because we know group 1 metals are always soluble. That was rule number 1. Then if I say, okay, what about the magnesium and the nitrate? Also there, nitrate, that's rule number 2. They are soluble as well. So because in this particular reaction, both products, the sodium sulfate would be aqueous and the magnesium nitrate would be aqueous. Because both are aqueous, both are soluble, that would mean that no reaction would occur. And all we do for that is put NR, which is short for no reaction. So nothing, we wouldn't see anything happen. No precipitate would form there. In the next reaction, though, we've got iron 3 chloride. So iron 3 partnered with the chloride. And then we've got sodium with the sulfide. Now, when you look at your ions, like I did for these first 2 examples here, when you look at your separate ions, right, the only ions that have subscripts are polyatomic ions, because of course that's part of the polyatomic. Notice when I wrote iron 3 chloride, I didn't put that 3 subscript on the chlorine, because that is a charge balance subscript, not a polyatomic ion subscript. Same thing over here, sodium sulfide, because the sulfur is -2, I need 2 sodiums to balance, but sodium isn't a polyatomic. So when I separate the ions, they don't have to balance charges anymore. I just want to look at one ion at a time. So the only ions that have subscripts are polyatomics. All right, so I've got my iron 3 and my chloride separate. I've got my sodium and my sulfide. When I put the iron and the sulfide together, the iron doesn't change its charge. It's still a +3. Sulfur is -2. If I crisscross here, I'd get Fe2S3. And then my other compound would be sodium +1 with chloride -1, so those are balanced, right? +1, -1. Now, I know that the sodium chloride will be aqueous because sodium is always aqueous, but let's check about the iron 3 sulfide. And when we got to rule number 9, which was about sulfides, it says most sulfides of transition metals like iron are insoluble, right? Insoluble means that that should form my solid. So we have a precipitate form here. We would see some kind of chemical change. PPT is short for precipitate. And now what we want to do is write the balanced equation. So we identified our ions. We predicted our products. We found that one would form a precipitate. And now we want to balance the equation by putting coefficients in front. No perfect place to start, but what I will say is when you have a compound on the product side that has subscripts for charge balance, that's usually a good place to start. So I needed 2 irons to make this iron 3 sulfide come together. On the reactant side, I only have 1 iron, so I'm going to put a 2 in front of FeCl3. I needed 3 sulfurs to make that iron 3 sulfide work. I only have 1 sulfur on the reactant side, so I'm going to put a 3 in front of sodium sulfide. Now I've got 3 times 2, 6 chlorines, 2 times 3, 6 sodiums, so a 6 in front of NaCl on the product side, and I now have my balanced equation. All right, one more to go here. Next example, I've got barium nitrate. So barium, alkaline earth metal, +2 charge, nitrate, NO3, -1. And I'm partnering that with sodium +1 and sulfate, SO4, -2. So I am going to look at putting barium with the sulfate. +2 -2 cancels out, 1-to-1 ratio. And then the sodium with the nitrate +1 -1 cancels out, so 1-to-1 ratio. Now again, sodium, you never even have to check the rules. It's always going to be soluble no matter what it's paired with. So let's check the sulfate. all right, with the barium. And what it said here was that most sulfates are soluble, but barium is an exception. Barium is insoluble. So that would be our precipitate, the barium sulfate. That would form our insoluble solid. Now, to balance, one barium on each side, one sulfate on each side, but I've got 2 sodiums and 2 nitrates on the reactant side, so I need a 2 in front of NaNO3 on the product side. All right, so 2 of those reactions we would see a chemical change, B and C, but for A, no reaction would occur, so that would just be a physical process, just mixing solutions, no chemical change, no new matter formed. All right, now one more example here on the page. It says, for the following reaction, predict the products in balance. And then what we're going to do is provide the complete and net ionic equations. All right, so what we've looked at so far, these are just balanced molecular equations. Molecular because everything is in a molecule or a compound format. When we look at this next example, we're going to do that, but then we're also going to look at total and net ionic equations. All right, so I've got zinc sulfate, so zinc plus 2 sulfate negative 2. Barium chloride plus 2 barium chloride is just -1. Again, that 2 subscript on the chlorine is not a polyatomic ion, it's a charge balance subscript, so I'm going to ignore that for now. On the product side, the zinc with the chloride, zinc is +2, chloride's -1, so it should be ZnCl2. And then the barium sulfate we saw in the previous example, +2 -2, should be BaSO4. Now we saw this in the last example that the barium sulfate is the precipitate, but let's double check the rules about zinc chloride. Rule here says salts containing chlorides are generally soluble. Exceptions are silver, lead, and mercurous. Zinc is not one of those exceptions, so this one would just be aqueous, the zinc chloride. Now to balance, everything is actually done here. 1 zinc, 1 zinc, 1 sulfate, 1 sulfate, 1 barium, 2 chlorines, 2 chlorines. And of course that happened because the 2 cations had the same charge. So that makes it easy to just swap. All right, that is, again, the balanced molecular equation. All right, molecular because, again, everything is in that compound format. When we break this up into a total ionic equation, what we want to do here is anything aqueous, we're going to break up into ions, right? Because really, if we think back to the sodium chloride dissolving in water, it doesn't stay sodium chloride. It turns into sodium ions and chloride ions. So in an ionic equation, that's really what we want to focus on. It's the ions that are in the solution. So anything aqueous, break up into the ions. Remember, ions must have their charges on them. So make sure that your ions have charges attached. And what's key here is any charge balance subscripts move to the front. All right, so let me show you what I mean by that. All right, so I'm starting with the zinc sulfate. All right, so when I break up zinc sulfate, I've got the zinc +2, and then the sulfate, which is SO4. Now that 4 isn't a charge balance subscript, that is part of the polyatomic, so that subscript has to stay in place. All right, so SO4 -2. For the second compound, the barium is a +2, and then the chloride, right, in the compound, that 2 is a charge balance 2. That's not a polyatomic ion, that's just chloride. So that 2 is going to move to the front of the chloride, so it's 2Cl -1. On the product side, the zinc chloride is still aqueous, so we still have that broken up, the zinc 2, and again, that chloride with the subscript of 2, the 2 moves to the front. All right, and then the barium sulfate, that one's the solid. So the solid, we stay together, right? That one always stays as the solid, as the compound. You don't break that up because, again, it didn't dissolve, right? It forms the precipitate. That's the chemical change that we would see, is that these 2 ions find each other and they make a compound that forms, right? That's the new matter that's formed. So that right there, that's the total ionic equation, right? Total, everything is there, but we've focused on the ions that are present because really that's more accurate. Now the net ionic equation, I think these were my favorite because they're the simplest. You just show what makes the solid. And so what we know is the chemical change was the formation of the barium sulfate. So what we need for that is the barium ion, and the sulfate polyatomic ion. Those two ions have to come together to make the barium sulfate. So 3 different ways to express the same reaction. Balanced molecular, everything is in a compound format, right? Total ionic, we have everything there, but everything that's aqueous is an ion separate from the other ion that was in the compound. We show them separate with the plus sign. All of our ions have charges, right? And the only thing that doesn't split is the precipitate. That stays as the solid. And then when we write the net ionic equation, we're just showing the chemical change, which was the formation of the solid. And when we write the net ionic equation, we remove what are called spectator ions. And those are the ions that don't do anything in the chemical reaction. They're just in the solution. So if you almost think about your total ionic equation as a math formula, and your arrow is like your equal sign, right? What happens when you have like terms on both sides of the equal side? You cancel them out, right? So I started this reaction with zinc ion, and when I ended, I had zinc ion. That says I didn't use any zinc. I came in with 2 chlorides, and I left with 2 chlorides, right? So I didn't use it. It didn't change. What did change, though, was the barium sulfate forming that precipitate. So that is a total and net ionic equation, all right? And so that we do that for double displacement reactions. All right, I think that actually is a good place. No, I'll do one more here. In the next example, looking at solution stoichiometry. With stoichiometry, your center point, again, is to go moles of A to moles of B, right? That's always our center point for all of our stoichiometry. So we saw this in the previous chapter, where if we had mass of a substance, we converted to moles using molar mass from the periodic table. Then we brought in our mole to mole ratio from the balanced equation. And then if we needed to get to grams of the product or something, we would use molar mass for that. So what's different now is we're going to be dealing with solutions. And for solutions, we typically don't measure the mass that we use, but the volume, right? How much volume of sodium chloride solution. To convert that to moles, we're going to use molarity, right? Because remember, molarity was moles per liter. So molarity is going to be our conversion factor that basically takes the place of molar mass, right? So instead of using molar mass, we're going to use molarity because we're dealing with volume instead of grams. So example here says, how many milliliters of a 0.100 molar silver nitrate solution would be needed to react with 750 milliliters of a 0.0250 molarity sodium chromate solution? And I've got the balanced double displacement reaction here. So it's asking me for a volume of silver nitrate, and it's giving me a molarity of 0.100 moles per liter. And then I'm reacting that with the sodium chromate. I've got 750 milliliters of that and a molarity of 0.0250 moles per liter. So as I mentioned on the first video, molarity is a conversion factor, right? It gives us moles per liter in that capital M. So what I always kind of did to remind myself was molarity is always my conversion factor, so I would always put it in parentheses. And then I'm looking for my volume of silver nitrate. So I'm going to be heading towards silver nitrate. And I'm going to start with the sodium chromate. So I'm going to use these quantities of sodium chromate to figure out my volume of silver nitrate that I'll use. Now when you go to start stoichiometry, you always want to start with a mass or a volume. For solutions, right, we're going to be starting with our volume. So I'm going to start with my 750 milliliters of sodium chromate. My molarity is defined as 0.0250 moles of sodium chromate per liter. That's how it's defined. But when you look at that, you can tell that your volume units are not canceling out. So an easy substitution is, we know that there are 1,000 milliliters in a liter. So in the denominator, we'll just put 1,000 milliliters instead of a liter, because they're the same thing, right? Then next step is we need our mole to mole ratio. So on the bottom, getting rid of sodium chromate, and on the top, going to silver nitrate. All right, and so for this, we pull in those coefficients from the balanced equation. So for every 1 sodium chromate, we need 2 silver nitrates. So the 2 subscript on top, or not subscript, sorry, coefficient for the silver nitrate. Then the last thing here is we need something that gets rid of moles of silver nitrate, and it goes to milliliters because that's what the question was looking for. All right, and again, moles per liter, that's molarity. So 0.100 moles per liter or 1,000 milliliters. So molarity is taking the place of molar mass because we're dealing with volumes instead of mass. And of course, in the middle, you always have your mole to mole ratio. So I'm going to take my 750 times 0.025 times 2, and then divide by 0.1. The thousands will cancel out. And to 3 significant figures, I get 375 milliliters of silver nitrate. So with molarity, you have to be a little bit careful with sig figs. Your volume that we started with had 4 sig figs, but both of the molarities only have 3 sig figs. And molarity, it's a little bit special in terms of the conversion factor. It acts like a measurement that way. You do have to, you look at that for the significant figures. So the molarity here limits the sig figs to only 3. So that's why we have to stop at 375. All right, that is a good place for me to stop for this video.